Good day, ladies and gentlemen, and you're all very welcome to this Saturday's presentation of one of our alternative sessions from the CNPS. Just to remind you, we hold these every fortnight, and in the intermediate weeks, we hope to have some sort of discussion or other, which might be of a more general nature, but nevertheless to do with the subject of fundamental physics and natural philosophy. My name is Ian Cowan, and I'm from Dublin, Ireland. So I'm hosting these sessions at the moment, and I think I've got my voice back. Unfortunately, 2 weeks ago I couldn't speak. I got laryngitis, but I think hopefully my voice is back and not too hoarse. I say good day to you because we have people from all over the world, although I think probably most of our participants will be from North America. And most people will be in via Facebook or YouTube. However, we do have a number of people in on what we call a green room, where they've logged in. I think we can host a maximum of 10 there, and we have maybe half a dozen today there, or maybe 5 or 6 today so far. And they are virtually present, if you like, because I think they're all 3,000 miles and more from me, but they're basically in the same room as me virtually, and I can bring them up when we arrive at the discussion, and we can have a more seasoned discussion between us all. The aim is basically to have a 50-50 split between the presentation and the discussion and Q&A. In other words, roughly 1 hour discussion and rather presentation, and 1 hour discussion. However, there's flexibility there. I think it was Jim himself who said that we were sometimes having a discussion which occupied maybe 3/4 of the 2 hours, and then we had very little time for discussion. So he suggested we cut it back, which is quite wise. So if the speaker only speaks for 50 minutes, that's fine. If he speaks for 1 hour 15 minutes, that's fine as well. But there's some flexibility there. Now, we're very honored and pleased to have Dr. James J. Keene again. He's reminded me that his name is of Irish origin as well, which I know, but he hasn't been to the Emerald Isle, actually, so we'll sort that out at some time. Jim is one of our regular participants, and he's been actually very forthcoming in helping us with these alternative sessions, because they haven't been running for very long. We've been, only running them for maybe 6 months or so, and sometimes we run out of sessions. And there are some people who are a bit shy, actually. Well, there may be very good reasons. I'll be speaking maybe in the next few weeks about giving a presentation from maybe 1 or 2 people who didn't want to speak, perhaps because their English wasn't their first language, and they didn't feel competent in it. So we'll be maybe showing some videos and so on. But anyway, James has been very forthcoming, as I say, not only giving us talks. Recently, I think he's given us about 4 talks, but this will be the 4th. But he's also actually offered to analyze some fundamental papers that we concentrated on. They sort of lit up when we had a look at them on the internet. Things like Peter Jackson we had a couple of years ago, and Henri Cornier some weeks ago as well. And Jim was brave enough actually to read those papers and to give us his take on the papers before the speakers spoke. And then the speakers spoke, and they said whether he had an eminent understanding of it, or he made a mess of it, or they disagreed. And in fact, even on the Peter Jackson one, Peter attended Jim's talk, and then he gave his own talk, but he was actually very complimenting of James's grasp of the fundamental question, which is actually not easy, because we all have our ideas and we try to express them clearly. I hope I expressed my ideas on longitudinal electrodynamic radiation clearly the other week, but it is difficult sometimes to grasp what everybody is getting at. Now today, James actually has talked in the past, and he has actually quite an amount of information online on the subject of binary mechanics and its successes, its significant successes in a number of areas of physics. But he's also talking about this lab, BML, Binary Mechanics Lab, and the software, which actually is available. He's made it freely available You can download it and use it, and he'll be obviously referring to that later. So Jim will be basically talking about the software components and their key methodological advances. Just one or two previews. He says there's a calculation ability where you can determine precise values of the basic physical parameters, such as displacement, electric and color, charge, etc. Then things like vacuum studies, where he's talking about a perfect vacuum, not empty space, absolute vacuum definition, vacuum energy content, virtual particles. And then also what he calls 0 Kelvin states. So you have the ground state, initially, particle definitions, ideal for light speed measurements. And then he has things like the parameter derivations, such as proton-electron mass ratio, alpha coupling constant, vacuum light speed, Coulomb force, the fundamental things where he's actually derived these from fundamental first principles. And finally, Jim will be addressing laser light simulation, not stimulation, simulation. Yes. Okay. So I've just read out what the summary is, and as usual, we will try to give Jim, roughly an hour or so to describe the things. He may want some feedback, and if he does, he can stop. And if any of you have really very urgent points that you didn't understand a word he said or something, you can maybe put a comment in and we'll try to answer it. But other than that, we would ask you to note any points you have and put them to Jim at the end of the discussion in about an hour's time, and we can have a full and frank discussion on that. So if that's all right, and I'll be bringing people up on the green room as well to discuss these matters later. And maybe if you have a very specific question that you really want answered, rather than discussions between you all, which are very welcome to engage in, they're most interesting, but you might just say, this is a question for Jim, so we don't miss it. So without further ado, I'm going to bring Jim and his slides up. I ought to mention before I do that when I bring it up, Jim is projecting his PowerPoint slides in his own sort of screen format, maximizing the screen. But with the StreamYard, you'll see his little picture in the left-hand corner of the screen. We can't get rid of that. If we do, he becomes silent. But if you wanted to maximize your own screen, I dare say on your own electronic component, on the bottom right-hand corner, there's sort of like a little square, and if you click on that, you'll maximize the screen. You'll probably get rid of the discussion, but you may want to do that. So Jim is up now, and Jim's slides are up. Although Jim doesn't see himself now, but he's vocal. You can hear him. I'm going to remove myself, and we look forward to your presentation, Jim.
Well, thank you for the wonderful introduction, E. And you summarize things very, very well. Okay. First, the title, of course, is Exploring Physics with Binary Mechanics Lab Software. Binary Mechanics Lab is located here in the Commonwealth of Dominica in the lovely Caribbean. It's called the Nature Island. You can download the free file, hotspot zip, here, as shown in the slide. You unzip the file into a directory. This is all you need to do. You could call the directory whatever you want. All programs are compiled with Hot Basic, of which I'm the author. And none of the programs change your Windows system directory or mess with your system in any way. They're entirely independent programs. For more recent Windows versions, set up the console window parameters for the simulator program, which is called hotspot.exe, as shown in this video. It's just a several-minute video. It shows you how to set up the console on your computer so that the characters and the layout are shown properly in more recent Windows versions. Other related videos are on BitChute.com, Binary Mechanics Lab. And here are the titles. There's a quick start and the interface tutorial. As Dr. Cohen pointed out, here is our outline for today. I won't go through it again right now. There's a lot of material in this presentation, so that during the video part of it, when you're watching the video, you can always pause the slide if you'd like more time. Right now, let's talk about the calculation ability of the software. Here is an image of what the simulator looks like. That's hotspot.exe. Here we're showing over 500,000 spots, and in the X-ray view, so that the lighter portions show greater density. Here is a histogram in XYZ of the distribution of one state locations in this view. To the right, we see to the left, we see a spectrum, which shows that there are different peaks, and the numbers here represent BMLS ticks. To the right is a whole bunch of data, which is written, most of it, into a file with each tick, so that this data can then be loaded into programs like Excel and analyzed. Here's a detail of some of the data that we have. Excuse me. It seems like I have a little laryngitis, perhaps in some sort of a spiritual communion with Dr. Cohen, who had the same thing last week. I won't go through all the details here, but here we have basically the number of particles. The electron is the left-handed lepton, and then the 3 right-handed quarks, and the summary of the number of actual protons in this volume. Here are the proportions of one states in each of the 8 particle types that you see here, which is matter on the left and antimatter. For example, the positron, which I'll be featuring in a moment, which is E plus right-handed. That's what the R stands for here. And their positions, both the standard deviation and the absolute position within the simulation for both the protons and the electrons, which is the E in 3 dimensions here, and other data. Okay, possible black body radiation depends upon quantum density. To the left of the image I just showed you were histograms of the spectrum of one state quanta leaving the simulation. When bits leave, they're called out bits, and these can be studied. It looks like as we increase quanta density, the quanta being a one state locus, from very low 0.033 on up, we see what looks like a curve, a black body radiation curve. And as we might expect, and by the way, this is the first time this data has been shown publicly, as we might expect, as the density, which means the energy content of the simulation increases, there are more bits leaving the borders of the simulation, which is what we're looking at, and the spectrum of these. And notice how the peak tends to rise here in the illustration, meaning higher frequency. So that here we may have an actual demonstration from the postulates of binary mechanics producing possible black body radiation curves indicating temperature. Now, if more work is done on this, one might be able to actually calibrate what these temperatures are at these particular quanta densities. If you press the help button, or the help key, H key, I should say, you're going to get a list of keys that you can press while the simulator is running, which gives help. Okay, now I'm going to quickly switch to another file. And just to do a quick review of the structure of space in binary mechanics, because you'll need to know a few things. When I say a bit locus, I mean a cubic volume of space at the quantized length L, which is one of the primary constants in binary mechanics. There are two types of loci, which are called the M bit and the L bit, which can only take values of 0 or 1. If three of these spot units, as they are so called, are combined in 3 dimensions now, we have what we call a spot. This happens to be the spot for an electron. And there are, in the complex amplitude in quantum mechanics, from which this was derived originally, we quantized quantum mechanics, basically. There are 3 binary values which can be swapped one way or the other, which creates a permutation of 8 types of spots. And here we see the 8 types of spots, where we have, again, the electron. The dark red, dark blue, and dark green are the matter d quarks, and the light values are the antimatter d quarks. And here we have the other side, which is the positron, which we can't see in the other illustration. Now, the basics of binary mechanics is that there are 3 primary constants for energy in kilograms, length, and time. And here are the equations which define the system state. I'm just going to breeze right past this. I'm just trying to introduce you to the idea that there are equations which define the system state and which do not contain any physical constants, so-called universal constants, which are, in fact, in my opinion, unexplained observations. And finally, these are the time development equations, which show how the system state changes with time. If you can define the system state and how it changes with time, you have a complete theory of what's called what is it called? A complete theory. And so these are the equations. Now I'm going to flip back to the other. Okay, next slide. Okay, one thing we discovered right off the bat in shortly after 2010 was that if we simply put only one state bit in the entire simulation in the right place, it cycles. Now, here's a listing of the positions, the change of positions, and there's a 21 tick cycle, which is called the proton cycle. Now, that doesn't mean much there. It's just a lot of data, but here we see that the one states are moving from a right-handed d quark to a left-handed d quark, and so forth down the line, and they come right back to the beginning again. And what do we get? we get what's called a bit cycle. This is the proton bit cycle. Here we have each locus is represented by a circle. And if we analyze the data I just showed you, which is an output file when you run the simulator, you can load it into your copy of Excel or other program as you may wish, excuse me, and get this cycle. Notice that there are, in the orange circles, there are 3 areas which involve the positron. You notice the gray here. At the periphery of this, what I call the proton or hadron bit cycle. This cycle explains confinement, or what's called the strong nuclear force. Now, now I'm supposed to show you something else. So let's escape from this and go to, I have the simulator running right now. It's paused, as you can see here. Here we have a single positron with 3 one-state L-type bits. There's 3. The total energy is 3, if you can see over here, and it is paused on cycle. You can run this by using the file in the BAT subdirectory called positron.txt. I'm now going to press the space bar, and we're going to see 3-bit cycles emanating from this positron. I pressed the C key previously so that when the cycle is over, it will pause. There we go, it paused, and it even made a little beep for us. Okay, now back to the slides. And I have to scoot ahead here. Okay, the so-called binding force, binding nucleons to form multi-nucleon atomic nuclei and ions, has been called the nuclear force. This is different from the strong force, which keeps quarks confined in the in a nucleon or proton, which we see now is due to the fact that there exists the proton bit cycle, which I just showed you. The positron-mediated proton motion mechanism described would clearly favor nucleon formation in spot cubes. That's the lower left cube I showed you with the 8 particles in it, adjacent to an existing nucleon spot cube, by feeding energy quanta into the adjacent spot cubes. This process might be crucial for nucleus formation. That is, this single mechanism may account for most known phenomena in nuclear physics, and thereby may become one of its most central fundamental principles. So now we have accounted for both the strong force, which keeps quarks confined to a spot cube or a proton cycle or nucleon, as the case may be, as you wish to view it. And in addition, the role of the positron in linking neighboring spot cubes in a very interesting way. You notice there are 3 outposts on the periphery of the proton bit cycle that were circled in orange in a previous illustration. Each of these connects with 3 other spot cubes which are adjacent. Probably almost everything we know in terms of phenomena in nuclear physics can be explained by these simple results obtained from the postulates of binary mechanics and programmed in a simulator so we can explore what is actually going on, or in other words, what are the consequences of the equations that I showed you for the system state and the its time development or evolution. How many BMLS ticks are in an attosecond, which is reportedly the greatest time resolution level achieved thus far by experimentalists? Well, an attosecond is about 1 to the 10 to the minus 18 seconds. One BMLS tick is about, in which time evolution laws are applied, the 4-bit operations is equal to 4t, where t is the primary time constant. And that's about this value here in terms of second. In other words, 1 attosecond, which is our greatest time resolution we can experimentalists have achieved, 1 attosecond is approximately 350,000 BMLS ticks. In other words, we get a resolution by the simulator which is simply not attainable yet in the lab. Here are some elementary particle energies versus the quanta or bit density, which can vary from 0, which would be absolute vacuum, to distinguish it from partial vacuum, which simply means the absence of nucleons, up to 1, where every single bit locus is in the 1 state. You can see that 3 types of particles, the right-handed d quarks, left-handed d quarks, which are the antimatter version, and the left-handed electron, which is our regular electron, and the right-handed one, which is the positron, you can see that they have different distributions over the range of bit density or 1 state density in the simulated volume. One thing we can measure by the data in the CSV files produced by the simulator is proton-electron distance. Here's an interesting study in which we analyzed the proton-electron distance and plotted it again versus 1 state energy density from 0 to 1, the same scale shown in the previous slide. We noticed that there are several ranges here. Here at this point here, we have the first protons actually emerging, which would be hydrogen, and then the first neutrons appear, and we have low Z atoms, and we stair-step distance reduction is equal to formation of neutrons and nuclei, at least in my interpretation of this data. And then what happens as we increase beyond about 0.6 energy density? Suddenly, the distance between protons and electrons in the simulation dramatically and rapidly increases. And this appears to be a phase of matter which we might call plasma. Increased proton-electron distance implies ionization. Finally, at very high energy densities, we get a lepton quark soup, where actual particles are barely distinguishable. It's basically just pure energy. Now let's look at vacuum studies. Perfect vacuum is not empty space. Absolute vacuum definition and so forth. Let's see what we have next. Okay, in this study, we populated the simulator with initial densities from absolute vacuum up to full maximum. Every single locus is in the 1 state. And we let it run in one of 3 modes. what's called the vacuum mode of the simulator simply means that when quanta leave the simulator, for example, producing various spectra, we saw the black body radiation spectrum a moment ago, producing various spectra, they're lost, okay? They're just gone from the simulation. And when all of those have left, we have basically our final density, which is composed of particles such as electrons and protons as defined in binary mechanics, and vacuum. Now you notice that this area under the pink curve is called perfect vacuum in ordinary physics. And yet it is populated with a huge number of one-state quanta. This is the so-called virtual particles, if you will, in conventional physics discussions. But here with the simulator, we can actually see that and study its details of what is actually occurring in perfect vacuum, and it's obviously not empty space. I'm going to skip this slide. This is the same scale again, showing the proton count. You notice that there's a threshold down here for the for getting any protons at all. And as we increase the density here, in the initial density, the final count on cooling to absolute zero is this amount, this high number of protons, which reduces roughly in the plasma portion of the curve, and dramatically decreases in the lepton quark phase of the curve. And here's a detail from the curve that I just showed you, with some standard errors included, showing that at 0.07 initial density appears to be the threshold where protons are first formed. This is called baryogenesis. And in fact, it involves the aggregation of quanta in bit cycles. And this is actually part of gravity. Gravity involves aggregation of energy in a more confined space. And this is exactly what's happening here. And so this is one of the mechanisms of gravity, one might say. Okay, let's go to 0 Kelvin states. What if we cool things to absolute zero? We're going to get some ground state particle definitions, which are ideal for light speed measurements. This is just a quick slide showing the S-file format, which is produced as outputs of the simulator. Each byte is a spot state, the least significant bits, and we have the two types of bits that I showed you before, excuse me, which can be in the 1 or 0 state. We count the ones, and so the total energy in this spot, shown here as an example, is 3. There are 3 ones. There are 2 M's and 1 L bit, and the inertia in the Y spot unit. If you have both the M and the L bit in the 1 state, we call that inertia. Now here is a output from the bit function analysis program at 0 Kelvin. And what are the results that we see? We see, for example, if the quanta that remain at 0 Kelvin, 0 Kelvin being defined as all of the quanta that want to leave the simulation by exiting at one of its borders are lost. So that what is left then is at a zero state. Those quanta that leave, quanta meaning a one state locus, when they leave, you're in a zero, you have zero radiation in the volume and zero particle motion in the volume. So 0 Kelvin can be simulated. It can't be achieved by experimentalists yet. We get very, very close, of course, but we can see with the simulator what happens if we could get to 0 Kelvin. And what do we see? Instead of some random distribution, and here's the density of the one state quanta that remain at 0 Kelvin in this particular simulation, it's very, very low. It's 0.006, very, very, very low. We're seeing a significant increase in the left-handed, which are the three antimatter d quarks, and the three matter d quarks. And down below here, if you can see down below, this is the positron, and this is the electron. So that we see that the bits, according to the laws of binary mechanics, if they're simply run in the form of a simulation, we see that the quanta organize themselves into these 8 particle types, which are the fundamental particles, which we can see in their ground state. Okay, now here we see what would be the maximum energy that you could have without any motion occurring. And I'm not sure what more to say about this slide. There are papers on all of this. So I'm just going to move along because there's a lot of material here in this presentation. But you see there is no inertia, which would be 2 of the bits in a spot unit, both being in the one state. There's no inertia, which means no movement of any kind from one spot unit to another. From one spot cube to another, and from one particle type to another. No motion at all in the 0 Kelvin state. That was the idea of this particular illustration. Okay, now let's go to parameter derivations. The proton-electron mass ratio, alpha coupling constant, and so forth. Let me check the time here. Okay, we're sort of on time. Excuse me for the cloudy voice. Let's look at the fine structure constant alpha. It depends upon quanta density. How do we define the fine structure constant? Well, it's the probability that a particle will interact with another particle. In other words, alpha is going to equal the occurrence of a scalar bit operation or a vector bit operation divided by the number of particles, the M0 here, which can actually move based upon fulfilling the criteria for a vector or scalar bit operation. So here's your definition on the left. Some data was analyzed, and we can see we have a sort of curve here, and here's the regression line for it, and the actual observed value of alpha, which is about 0.00729 right here in this area here, shows that this bit density here is probably close to what we call standard pressure and temperature at sea level, where a lot of these experiments are done nominally speaking. You can see the results are all significant because we have standard errors in both directions to show you that this is actually a curve. And what we're seeing here is that the so-called universal constant alpha, which is the coupling constant for the electron and the photon, depends upon quanta density. In other words, it's not really a constant in short. Now let's look at the proton-electron mass ratio. It depends upon quanta density also. How do we measure this, the proton-electron mass ratio? Well, in the data that the simulator outputs to a file, which then can be loaded and analyzed in whatever statistics program you want to use, we have the amount of displacement of both protons and electron particles, okay? The protons would be all of those particles, the right and left d quarks and the positron, which form the proton bit cycle that I showed you. The electrons, of course, are those confined to the electron cycle. Now, here we see that so by assuming, if we assume that the forces acting upon the protons and electrons, whether they be electromagnetic field or whatever it might be, are about the same for the proton and the electron, we can then use the amount of movement of the proton compared to that of the electron to estimate the proton-electron mass ratio. Because the larger the mass, the less movement for a given force, right? So here we have again the fact that the observed proton-electron mass ratio, which in books is down here, it's shown about 1,836.15, shown here with an arrow roughly in the diagram. We see that that also is not a constant. In fact, that it depends upon quanta density. Here's the proton-electron mass ratio plotted over a wide range. And we see here that around this area here is where the so-called constant proton-electron mass ratio is, but we can see that it definitely is linked to the bit density or energy density of the volume, which is a new result again of binary mechanics. Here is the experiment showing unidirectional measurement of light speed in perfect vacuum at 0 Kelvin is an ideal situation to measure light speed, since movement of particles is 0 and electromagnetic radiation pre-existing in the simulated initial state is also 0. We can inject quanta on one side of the simulator and look at the arrival of quanta at the other side and thereby measure the speed of light. It turns out that we can measure the speed of light and find out that it is about the value that is reported for the vacuum speed of light. In other words, we've derived the speed of light without using any constant whatsoever. This is the only theory in physics known to me, the author, where you don't input measured observations, which are unexplained, which are called universal constants, in order to get results. There are no inputs of any unexplained observations in this data. It is solely from the principles of the system state definition and time evolution that I showed you in binary mechanics, and we get the actual measured light speed out of it. Here is a simple diagram showing what happens when we have the scalar bit operation, where two adjacent spot units are both in the one state. The m bits here, shown as circles, are in the one state. And at time equals 1, this can cause the one state m bit to shift to the L bit location, which is the second kind of location in a spot unit. The lower one here does not show any motion because the destination location must be 0. In this case, it's in the one state as shown here. And so therefore there is no movement of the lower bit. If both locations are empty, both will move to the L bit location. From this, we can calculate the Coulomb force and electric charge. Because we know the distance and we know the charge at m and can calculate what it is. And this again is a first of binary mechanics. So we have in summary a physical constants derivation tree where the primary constants m, l, and t can give you the secondary, what I call secondary constants, the electron mass, vacuum light speed, Planck's constant h, which includes of course, the intrinsic electron and proton spin, the elementary charge E, which is based upon the elemental charge C, which is 1/3 of the elementary charge E, and finally the intrinsic electron magnetic moment. Okay, laser light simulation. Let me check my time. Okay, we're doing good. Let's see what we have here. Okay, standing waves in 3 dimensions in the quanta density box mode. Okay, I mentioned that there's 3 modes that the simulator can be run in. One is the vacuum mode, which we have discussed, which means that quanta exiting the simulation are simply lost. They're gone, and the simulation proceeds with whatever quanta are left in the simulated volume. The second mode, which we can talk about, is shown here, is called the box mode, where the sides, the 6 sides of the cubic simulated volume reflect bits so that there's no bits lost, except for a brief time where they're in the process of being reflected back into the simulated volume. Here we see that in the box mode, one might expect something. Well, you get standing waves, which are shown by this XYZ density histogram, which is the histogram of the distribution of one states from top to bottom, right to left, and front to rear in this simulation. Now, during a run, if you press the Y key, you will get a histogram showing just the Y dimension in those cases where you want to have only one dimension summarized in the histogram. But here you can see quite clearly that the simulator has detected standing waves in 3 dimensions, and the interval 1, 2, 3, 4 spot cubes between each of these peaks is quite remarkable. Here's another example of standing waves at a different bit density, a little bit higher, closer to our range of standard standard temperature and pressure, I should say, excuse me. And here again, we see peaks which are equidistant, and it's sort of a remarkable feature of the box mode. The third mode happens to be the what's called random mode, which means that when quanta leave the simulated volume, they yes, they are lost, but the simulator program keeps track of how many are leaving, and it will inject on all six sides of the simulator at random locations a sufficient number of one state quanta to, in sort of a negative feedback loop, if you will, to maintain a homeostasis or a relatively constant quanta density in the volume. It's sort of as if you're looking at what would happen in the simulated volume if it were surrounded by unsimulated volume, but at roughly the same quanta density. And that's called the random mode. Now, some laser experimental data. Here's a detail. What we have here is the bits exiting the simulation in each of the six faces of the spot cube. And you notice that when we run the experiment one of the simulator, called the laser experiment, we get a huge asymmetry here, where in the y dimension, a lot of quanta are bouncing off the top and the bottom of the simulated volume, with relatively few on the right and the left. I've seen cases where the right and the left actually go down to zero or near zero, and you only have quanta leaving the top and the bottom, and these can become synchronized, in other words, coherent wave shown in the histogram and in the simulator. And this is your laser experiment. Now, how is this done? In the laser experiment, the top and the bottom faces, two of the six faces, are in the box mode. In other words, they will reflect outgoing one state loci, which I call quanta, back into the simulated volume. Whereas the four faces to the sides, right, left, front, and back, are in the random mode. In other words, they are going to inject quanta randomly only on those front, back, and right, left surfaces of the simulated volume to maintain a certain energy level within the volume. What we get then is an amazing result that the almost all of the quanta become oriented either up or down of the L-type bits, okay, and right or left in the X, Y, and Z configuration. So that is our laser experiment. Now we're going to talk a little bit about magnetic monopoles. Physicists have long talked about the electric monopoles, which would be the the electron and the positron, or the proton and the neutron, or in other words, plus and minus charge. What about that's the M-type bits I showed you previously? Now, what about the L-type bits? Those are your bits which indicate directionality, and they can be either up or down. And we see that the proton Y displacement depends upon the direction of injected L-type bits, which are can be considered to be a magnetic field pulse. The same is true for the electron, where we get the same results. In other words, the proton and the electron have opposite charges, but they're moved in the same direction according to the injected magnetic pulse consisting of L-type bits in the simulation. Okay, the BMLS interface setup. Let's go back a minute here. So what we're talking about here is that we may have in fact discovered and demonstrated the phenomena long sought after by physicists of magnetic monopoles, which are simply the L-type loci in the one state in binary mechanics lore. Okay, here is the, for those of you who like Windows, and sorry for the console views in the previous illustration, let me say that when we're making software to do experiments in a laboratory, we're not interested in beauty. We're interested in functionality. Does it work? Is it correct? Is it giving us the correct values? And so forth. How pretty it looks and even how easy it is to use are not the primary considerations in a scientific laboratory. However, I did make this prettier little program called the Binary Mechanics Lab Simulator Interface, which allows you to do a number of things to set up experiments, and you can enter parameters as shown above and set the initial state and then save the parameters and run simulator. That's what you do. So you notice that we can choose the plane mode. The plane mode of the display was shown in the positron example, showing 3 bit cycles arising from a single positron. The X-ray mode is the X-ray views that you've seen in other illustrations. We can check box mode if we want to run it that way, or random mode. If neither is checked, we're in vacuum mode, which means all bits are lost for exiting the volume, are lost for forever, and we eventually get down to 0 Kelvin. There's the left gun and right gun, which we can activate, for example, in light speed measurements and so forth. We can choose the bit density, and we can set the initial states. In this one, we're only going to select with almost 100% probability the positron. It's checked. All the others aren't checked. And the 3 L-type bits that consist of the positron are here, and here's the range that we're going to populate and the bit operation order that we're going to use. The experiment we could choose here, or in this case, just set it to 0. If we choose these parameters, if you download the software and run the Binary Mechanics Lab Simulator Interface Pro program, all you have to do is set the initial state as shown here, then, which is clicking this button here, and then you would save the parameters, click here, and then run the simulator, click here, and you'll get what I showed you in the example that was running in real time during this presentation. Okay, here's a big overview of everything we've talked about in terms of the interrelationships amongst the various parts of the software set. The interface is called the BMLS execute, and it can set the parameters in a text file, and we can run, when it runs, we're going to then run hotspot execute. We can create new input parameters with the BMLS interface, or we can manually do this by just running hotspot by itself, which is the BMLS simulator. And we can continue to add objects. If we say yes, we can go back and manually add more objects and so forth. It's much easier to use the BMLS interface to do this. Now we can run the hotspot execute, and when we do this, we get at startup in the INI subdirectory what are called MAT files, which is a representation of the simulated space. And at exit, we get in the DAT subdirectory a mat file of the final state on exit, as well as what's called an S format file. The S format files are inputs to the bit function analysis program that I showed you, which defined the 8 particles at the 0 Kelvin state, and which confirmed that the prediction that there would be 8. And the at exit also we complete and close the data file which has dozens of parameters which can be loaded into a spreadsheet or custom analysis program that you've written. For example, the out bits, which are bit one state quanta leaving the simulated volume, are recorded in the output file. And so in this output file, any spectrum analysis program that you want to run can be run inputting this data, because you have each row of the file is one BMLS tick, which is the application of the 4-bit operations to the simulated volume data. Okay, what do we have next? Okay, the batch mode input parameters, the text file format. When you run, let's go back. When you run the interface, it creates a text file which can be done manually and edited manually. And the contents of this text file are here, and there's a lot of detail, but it basically tells the simulator hotspot.execute what to do. And so that you can, in batch mode with the simulator, create a number of runs of the simulator and have it run all night or all week or whatever, creating data where you vary one or another parameter as an independent variable in your experiments, and get the results out, and finally just entirely automated. That's the purpose of this slide here, and this is the details of it. Okay, I guess that's the end of this presentation. As far as we go, we can just click space here and let this guy run a little bit. Here you see the amazing result. You notice that with each proton bit cycle, there are 3 positron locations, and each of these 3 positron locations in fact connect to 3 other spot cubes which are neighboring. And this is the amazing result of the role of the positron. You notice in binary mechanics that the positron is not exactly equal and opposite in functionality to the electron, as the standard model, in my opinion, thank you, wrongly asserts. In other words, the matter and the antimatter are asymmetrical and different. Oh, okay, Ian, take it away. I guess I should go out of share screen mode if I'm not already out of it.
Thank you. I think I have to do a few things
Let's
here,
see.
Jim, to sort it
How
out.
do I get out of screen?
So I can, yeah.
There we go.
You've done it. You've done it. I thought I had to do it. Well, thank you very, very much for that stimulating presentation. And you're always bang on time. I mean, we started a little late, and you sort of, I think you were trying to make up a bit of time at the end of the session, but it's great to be just after well, 4 o'clock.
Part of my reason for hoarseness today is not only empathy with your hoarseness last week, or 2 weeks ago, I should say, but too much smoking. So I'll take a break here and light a cigarette while you proceed.
Right. And I didn't actually mention to some people that we had some discussions because there were 2 upcoming talks. There was my one and there was Jim's. And in fact, Jim was going to give it 2 weeks ago, and I was going to give it today. And then he contacted me to say he had some bug, and he didn't think he'd be able to prepare slides or work or anything. So I said, well, I'll come in and maybe we'll swap around, and in 2 weeks' time you should be all right. But hey presto, I get the I get the bug, and I don't smoke cigarettes, but I do take the occasional pipe, and I actually was smoking my pipe, and I don't know if that caused it or it didn't. I'm not sure, but anyway, I got laryngitis, and I was able to give the talk. I think, although it was rather weak, and anyway, you weren't too bad today, Jim. But
yeah, I was miserable. Thanks for standing into me. I've recovered from that, and I really had some kind of a flu. That's what it was.
Okay, and these can take weeks to clear up completely. So we are grateful to you for having come in today. And it was actually quite a stimulating talk, and I never cease to be amazed at how individual scientists in our group can perform very fundamental research and get a lot of information and results. I mean, if a talk like this had been given by maybe an academic who had resources of university laboratories, or maybe a private company, I might have been less amazed, because they have a lot of facilities at their disposal. But we don't, and I'm actually quite amazed. We had Eric Reed the other week, and I was amazed at what he had done as almost a one-man show. But I'm actually quite amazed at the significant development which has gone into this subject of binary mechanics, and the software and the simulation and all the laboratory work and so on, which has been done. We have a few questions which have come up on the general chat, which I'll put to Jim presently, better than trying to answer it between ourselves. But just maybe a few observations. I noted, maybe generally, I noted, Jim, that you said that your results were at variance with the standard model. But I'm wondering more generally, would the results coming out of your whole BML system be more in tune with some classical concepts of natural philosophy rather than modern concepts? Because many of us in the dissident world have actually found that, my work, for example, is nearer to the concept of classical electromagnetism than the modern special relativity and so on. So I'm wondering, is there a simple answer to that? And you did talk about the standard model, of course, and how you disagree with some aspects of that. Maybe I'll just mention one or two other observations. You can comment maybe on the lot, and then we can maybe deal with one or two of the questions which have been coming in. Let me see. Yeah, you mentioned the magnetic monopoles. That might be an example of a difference where there is maybe more of an analogy between the electric polarity and the magnetic opposites than maybe is given credence in normal physics. I was also interested in actually, this might indicate how you've been so successful in providing the results and the spreadsheets and the graphs and so on, because you said, in laboratory work, we're dismissing beauty. And I think actually Einstein mentions in one of the popular books on relativity that he's leaving matters of elegance to the cobbler and the tailor. And I also Alfred O'Rahilly, who wrote this magnum opus on electromagnetics, will be coming back to that maybe in the coming week, because I'm in discussion at the moment with a number of people like Harry and Dennis, but also some gentleman in Wales who's actually doing some research in this area. But anyway, just in passing, I mentioned that O'Rahilly, deprecates the too much focus on beauty and fashion, and he said he a bit sarcastic. He said, "Well, it's not only in millinery that people are concerned with beauty and fashion. It also influences science." So Maybe just before we go to the questions, I don't know if you have any comment on that about your fundamental disagreement with some of the modern physics ideas, Jim.
Well, the basic disagreement is that we're quantizing space, time, and energy in binary mechanics, so that we're leaving the classic continuous space-time theory behind. And it has failed, and I think it is destined to fail really forever. Oh, I'm very small now.
I'm trying to experiment. I was going to make myself small to keep in, but I couldn't do that.
That's okay. Keep yourself in, so that in the case of the standard model, it's basically a summarization of data observations, which a lot of brilliant people have done over many years to determine 3 generations of particles, which binary mechanics fully accounts for, by the way. And it requires the input of nearly 24 unexplained observations, which are called constants, like the speed of light, the electric charge, and so forth, Planck's constant, and what have you. In other words, the standard model requires the input of unexplained observations. And so its conclusions are therefore unexplained also, logically speaking. Whereas the binary mechanics goes the other way and says, what are the fundamental postulates that we need without using any of these fundamental constants? And can these postulates produce the values of the fundamental constants, which then become explained observations as opposed to unexplained observations? And so it's a matter of going one way or the other. I'm trying to see. Do I see my 2 fingers pointing in opposite directions here? Binary mechanics goes one way, and standard model goes the other. And recently, in my most recent video on BitChute, I actually posit that without the quantization of space, time, and energy, it will not be possible to make any basic fundamental advances in physics. Not only have the assumption of continuous space and time failed to account for the values, the measured values of these constants, but they will continue to fail. In other words, it's a fool's game that will lead to no significant advance in physics. Regarding basics of what you're saying of going back to certain classical basic ideas, study of the scalar and vector bit operations, I think, will reveal that the quantization which I did of those was really based upon the classical ideas of electromagnetism.
Oh, okay, well, it's important to realize that, because I think some people might jump to the conclusion that your ideas are more consistent with modern physics because of the quantization, the quantum theory and even the word quantum and quanta and so on. But I think you've made it an important point there. There are a couple of points here. Franklin actually has been making them, and we're not getting many comments in today, but normally they're people just chatting among themselves. He says, is there any experimental evidence of a variable proton to electron mass ratio that matches your graph, presumably?
I'm not sure if what Franklin is referring to is the fact that the proton-electron mass ratio changes with overall bit density. I'm not sure what that evidence might be, which one of the great things about binary mechanics is that it produces, unlike, say, string theory, which is a complete fool's rush on on idiocy, I say. Uh, Binary mechanics produces a large number of hypotheses, many of which may be in fact testable. So this is where the great minds need to be in, say, our our group. Instead of just simply reiterating over and over why classical theories like special and general relativity don't work, why not go into the future and actually design experiments which test some of these hypotheses? So Franklin, that's a great idea. Right off the top of my head, right here in this session, I can't think of an experiment, but certainly let's think of experiments to test that theory. In other words, one thing I would love is someone to absolutely exclude or disprove binary mechanics in a very fundamental way, so that one of its predictions is the proton-electron mass ratio changes with respect to overall quantum density in the environment. And if that prediction is not verified by experiment, then that might exclude quantum binary mechanics, which would be wonderful. I'd save a whole lot of time not working on it anymore.
Well, that's the scientific attitude, certainly, to accept that one may be wrong. But I don't understand. I think he's saying, how can it depend upon quantum density? Indeed, but I think he means, I thought that the P mass is a measured constant. He said, I didn't think. I'm not sure that makes sense. I think he's saying that he thought it was a measured constant. But anyway, that's perhaps a subject for further work, and I'm glad that you're open to that. There's one more he added here.
Well, let me address that quickly, if I may, because Franklin is a great mind to pay attention to. At lower bit densities, there might be less resistance to motion of protons, and therefore their mass would be evaluated to be less. At higher bit densities, the locations adjacent to any particular proton or nucleon are relatively have an increased abundance of one states. In binary mechanics, any particular locus can only have one and only one quanta of energy in it. That's why the M and L values are either only 0 or 1. Therefore, if in the environment of, say, a proton, more of the adjacent loci are in the one state, the proton simply couldn't move, or would need a greater potential driving it to move, which would then be judged as a greater mass, according to the traditional force equals mass times acceleration expression of Newton. So there's, one of your basic concepts of classical physics, which I use there.
Indeed, yes, Newton's second law.
So there's sort of an intuitive explanation of the phenomena, but Franklin is right to point out, let's take that and think about it more, and perhaps we can actually demonstrate this in the laboratory. Or let's say hydrogen gas, for example. Is it easier to move a single ion of hydrogen, let's say, which would be just a proton, in deep outer space, where there's relatively few quanta, few loci in the one state? And if so, it would be judged to have a lesser mass. Likewise, in the middle of, say, a very heavy gold bar, which is full of quanta in the one state, represented by the heavy nuclei of the gold atom, it could be that protons find greater difficulty to move because binary mechanics requires that no quanta can move unless there is a destination loci in the zero state, in other words, which is empty, because you can't have two quanta in one loci. So there's an intuitive explanation of it, but let's think about doing some experiments, because one thing that I find in some of the CNPNS talk is that we, like some people say, I won't mention any names, but some people say, well, any theory is okay and they're all equally true and nothing can be proven or disproven or whatever. And this is really, to me, an anti-science view. I'm going to take the opportunity to say that here, because certain experiments, yes, can exclude certain theories. And likewise, certain theories have more confirmed predictions than others, and therefore carry more weight. So it's not all equal, and it's not, oh, you can say anything you want. It depends upon the evidence.
And indeed, it takes only one contradictory piece of evidence to disprove a theory. You can have thousands of predictions that it appears to conform to, but one contradiction can disprove.
Exactly. You stated more succinctly what I was trying to say. Thank you.
Thank you. And Cornelius just says a better question is, what gives the electron and all particles mass? So I don't know if you're going to start bringing in what's his name, the Scottish physicist, the particle. I've just forgotten it.
Well, binary mechanics is a step in the road toward our understanding of the physical universe. It's not the final step at all. And if we go back to my previous talk, which defined the idea that space is a structured medium with cubic loci, and it can only contain one unit of energy, or 0 units of energy. In other words, be in a one state or a zero state. We're not defining what that thing is. We're just saying it's a one state. We don't know what that thing is, but it certainly does relate to the idea of mass, as shown by the equations which I published in the constants derivation tree, which I showed. And one can get more detail on this in the binary mechanics fact article, as well as the binary mechanics postulates article on my website.
So just being a bit pointed, and I've remembered the name, I just couldn't recall there. Do you think that the Higgs is a fake? Or have you?
Oh, yes. It's very interesting that the Higgs, I forget what it's called right at the moment, but there are two, it consists of a quantity of two complex numbers. And it's interesting, in my derivation of binary mechanics from classical or non-complete, incomplete quantum mechanics, that these two complex numbers in the so-called Higgs field correspond to spot units. And it's interesting that the Higgs idea then involved the juxtaposition in of two spot units, which is exactly what occurs in binary mechanics in the strong bit operation within each spot, which is composed of 3 spot units. So any pair of those can have an exchange of a one state, and that is our strong force. And that's what confines mass to the proton bit cycle and the electron bit cycle, by the way. And that's as far as we go. So there's sort of an analogy there, but the Higgs mechanism is a very clumsy way to express what's actually going on.
And finally, on Franklin's point, I don't know if you have any observation to make on this, Jim. I'm not sure what he's getting at. Is he talking about relativistic changes? He says the mass of the electron has been experimentally verified to be variable, depending upon the matter environment in which it is traveling.
Well, perhaps we should ask Franklin to present that experiment. I'd love to see it.
Yeah.
And I could comment on it, not knowing what the experiment actually did, or
I don't think he's talking about the relativistic experiments, but anyway, he could come back to that at a later stage. I really must ask: is there anybody in the green room who wants to talk? Yeah, Denny, I'm glad you've put your hand up, because there were a couple of others. I think we had about 5 people, and we only have. Well, I'm counting myself and Jim. So I think we had Nick, but he seems to have gone. And I don't know if he's through on the media now. And people like Harry frequently come in on the media, but then they join on the green room. But the moment, all we have is Denny. So I'm going to bring Denny up now. Good day, Denny. You're very welcome. Have you got any particular point you'd like to raise?
Jim, you seem to have produced the speed of light from your axioms of your system, but your axioms of your system are based on Dirac spinors, if I understand it correctly. Now, Dirac believed in Maxwell's equations, as far as I've been able to determine, and so the speed of light, it comes out of those. And well, we're going to have some talks soon on longitudinal radiation as opposed to the usual transverse. And the velocity of this radiation may be different than the velocity of the C velocity of our usual transverse radiation. If that's the case, how would that fit into your binary mechanics model?
Well, there's nothing in the binary mechanics model that prevents measurement of different speeds of light. For example, we have refraction, where light is slowed down when it passes through a region of higher energy density, I would say, some solid material, for example, and or liquid material. And so what I would say is that the basic speed of light is conditioned by the environment in which you measure it. I measured it in what I tried to simulate as an initial state of absolute 0 Kelvin, which would mean in my context that there's no particle motion and no electromagnetic radiation in the simulated volume to begin with. And of course, we inject radiation on one side of the simulation and count its arrival at the other side in that particular situation. And we come up to pretty much the exact value for the so-called vacuum speed of light in classical physics. The other possible velocities, those are not excluded by binary mechanics. It would depend upon what is the medium through which the light is being transmitted. And so I would say that. The second point is that I am not aware of any derivation of the speed of light from Maxwell's equations, which does not depend upon use of some other unexplained constant, such as electric charge, for example. So I can't comment on that since I'm simply not aware of that. As far as I know, my work is the only work which produces a vacuum speed of light, which is similar to the value which has been traditionally measured, called the vacuum speed of light, without requiring input of any other unexplained observation or so-called fundamental constant. So if there is such a work, I would love to see it, but I've not seen it and I'm not aware of it.
Well,
as far as I know, my work is the only work that produces the speed of light without using other unexplained constants.
But if you injected longitudinal radiation at the absolute zero instead of transverse radiation, and it turned out that had a different velocity, how would your mechanics, binary mechanics, account for that?
What was that last phrase, Danny? How would what?
Could you repeat that, sir? Mechanics account for that.
How?
So if I understand what Danny's saying, just correct me if I'm wrong. So you have a constant value which comes out of the soup, if you like. But we're talking about, say we postulate the longitudinal electrodynamic radiation, which I've talked about and we'll be looking at maybe in the coming weeks. And suppose that has a constant speed, a speed which is different from the transverse speed of light. And we've no reason to believe it is the same. We don't know yet, but perhaps a different speed. Would that come out of binary mechanics? Or if it did, how would it come out of binary mechanics? I think that's basically what Dennis...
Well, presumably one would have to design an experiment to do this. Now, in the slide that I showed for the light speed measurement, and I presented that here previously as well as the whole presentation, in that experiment now, quanta were injected over a period of time, some 72 binary. And so you might say that was longitudinal radiation being injected. In other words, if we had just injected, let's say, for one tick, then we might be talking about perhaps the kind of plane wave, if you will, that we're familiar with from things like Maxwell's equations, where you have the electric field and the magnetic field oscillating perpendicular to each other and transverse to the direction of propagation. But you see, in my experiment, a number of quanta were injected over a significant amount of time. And as the curve showed, hundreds of those quanta arrive at the other side, and the calculations were done to determine the speed of transmission of that signal. So my point here, Denny, and I appreciate your comment greatly, is that it gets down maybe to how we operationally define terms. It could be that what I was injecting in my experiment, you might or others might argue, or even myself, was a longitudinal wave, because it was injecting quanta on one side of the simulated volume for a period of time. Okay, each cycle of the simulated new quanta were injected over 72 ticks in this particular experiment that I showed. So it gets it gets down to defining what is a longitudinal wave and how would it be defined in the binary mechanics setting. Does this make sense, sir?
Well, to a certain extent it does, but it seems like if you say, well, what if it really was longitudinal radiation that was injected? Well, then you get the same value of C, but if experimentally it turns out to be C plus delta, or where delta is not small, then you're back to square one, so to speak.
Well, I would just say that we've learned something.
Yes.
Yes, quite so. But following from that, I might just say, or ask, basically, if I may, we talk about other forces. I mean, the old chestnut of, say, the speed of gravity, following, the work of Van Flandern and so on. What one might work out a theoretical basis for it being orders of magnitude greater than the speed of light. Or similarly, in some of my analyses, we would have the establishment of things like electrostatic fields would take place at much greater speeds than that of light. So I'm not sure if that would come out of the wash in your analysis, Jim. Looking at these, say the speed of gravity.
Let me point out this, that if you go through my presentation, it may give the impression, oh my, I know a great deal. What I would prefer the message to be is that my raising a lot of questions of things we don't really know yet. But we're going in the right direction because we're able to make predictions which in many cases are testable. Now, since binary mechanics is basically in the category of a theory of everything, that's the term that I couldn't quite come to mind during my presentation that I was looking for. It covers all areas of physics. One little guy like me can't be a super expert in every single area of physics. It's difficult to be an expert even in one little area. So there's opportunity for many investigators to consider these issues and define experiments which will either exclude or include by the binary mechanics theory of everything. Because basically, binary mechanics is stating that there is no phenomena which cannot be accounted for by its postulates. It's that simple. And if there's a single phenomena which cannot be accounted for by its postulates, that would exclude binary mechanics, or at least say that there's something wrong with it in some way which needs fixing. We seem to have frozen.
Well,
sorry, you couldn't hear what I was saying because I wasn't up.
Yeah, we're going to have to find out we're going to have to find out what the velocity of longitudinal radiation is before we can go much further.
Right.
Well, I have several papers on the velocity of light and several videos on the same, and that's the state that I'm at now. Much of the work needs to be replicated that I've done. The simulator is free, it can be downloaded, and this work can be done. For example, in the magnetic monopole section of my talk, I showed one trial, which was sort of a jagged, wiggly curves of the proton and electron displacements. They were in the right direction. Statistically, they were significant because you could take every single point and consider it as a result, aggregate them, and do a statistical test and say you wouldn't get that result by chance. However, if those experiments were repeated with a number of trials and averaged, then the curves could be smoothed and more detailed conclusions might be drawn. So that in terms of the speed of light, again, I know of no theory that can produce the speed of light as binary mechanics has without use of other unexplained constants.
Well,
Anything
no,
further, Denny?
no, that's about it. I think.
Okay, well, thank you very much. Thanks indeed. I'll bring you down just for a moment. If you want to come back, there will be a few more minutes left. Okay. Basically, just something occurring to me, is going off a bit of a tangent there, Jim, is presumably you've prepared all this software yourself.
Correct.
Yeah, it's quite a marathon task, but you've made it available free of charge. Now, that's very admirable, and one may question why. But also, looking at it maybe from a positive point of view, is I'm wondering, have a number of people been in a position to download the software and perform some simulations with it? Because if so, it would appear to me that you would have at your disposal a team of people who could feed in information, just like sort of the astronomical observational software, which is made available freely, and they're asking people to go in and put stuff in. It would appear to me that you could have hundreds of people supplying information to you, which could help in your analysis. I mean, life is very short. One person acting on his own. So I'm just wondering, have you any experience of people downloading the software and perhaps getting some results from it?
Well, not so far that I'm aware of. I'm aware that there are a lot of downloads. There's been hundreds and hundreds in the recent months, actually, of views to my website, and also views to the videos I produced. And so there might be more interest in it. The software won't necessarily be free forever. So if you want it, you should get it now. Plus, the software is developed to do certain experiments. If Denny or other people come up with an idea with regard to light speed, or frankly with respect to proton-electron mass and so forth, it could be new features need to be written into the software to enable it to do the experiments that are required. Also, there's, like, for example, I've analyzed lunar laser ranging data as well as the GRACE satellite data, which is produced by others, multi-million, if not billion-dollar efforts to confirm predictions of binary mechanics concerning gravity as not being a primary force and being surface temperature dependent. There is a whole set of Grail data of twin satellites circling the moon, which is similar to the GRACE data, which is available to download, and anybody can download that data to try to confirm my predictions of binary mechanics yet again, using other people's data. So the point I would make is that oftentimes the software needs to be developed to save certain data points or what have you needed to do a particular new analysis. And I'm open to interaction with others to use the software and further develop it to enable it to do experiments which perhaps today it's incapable of doing. Or not capable, I should say.
Just by the way, I think Franklin put in a note which sort of clarified some of his earlier comments, that he was thinking of electrons moving in regions of different charge and thereby changing mass. I think that's what he was talking about, rather than relativity. But anyway, it's still something that could be investigated further.
You see, but how would you know that they've changed in mass? If you analyze the regions of different charge, if you will, those would accelerate the electron in different ways. So it's by the way, those experiments can be done with the simulator. You can set up a volume and poke in your initial state some extra charge, or plus or minus here or there, and follow the path of electrons as a result of that. But a change in the trajectory of those electrons is not going to necessarily say that they've changed in mass in terms of the fundamental primary constant m, which I use for a proxy for energy as measured in kilograms. So those experiments can be done right now. Yeah, so, it's just a matter of who wants to make the discoveries. I found that every time I've tried to debunk binary mechanics myself, for example, in the study of gravity, I found instead a new discovery. So that I welcome people to come in and try to do experiments or cite experiments that others have done without using binary mechanics, just their data, to further examine the veracity of its theory and its postulates.
And another thing, I just come in, and I'm not sure if my understanding of it would be correct, Jim, but MC is saying, how is your explanation of the speed of light different from the ether's explanation? Well, I mean, you're not contradicting the classical derivation of the speed of light dependent upon electromagnetic phenomena like electric conductivity and magnetic permittivity and permeability. You're just saying, as I understand it, that your derivation doesn't depend on any other previous derivations. But you're not contradicting the ether sort of derivation, I take it, are you?
No. Okay. No, not at all. It's just that, do you want to accept unexplained observations as inputs into your work or one's work in physics? My answer is no, because they're unexplained observations. The purpose of physics is to explain unexplained observations, not to simply use them as input parameters in other work, which is going to really create more unexplained observations, as it were.
Okay. Yeah, there's some discussion going on about spherical wave patterns and, I don't know, inertial versus gravitational mass and so on. And I think Franklin was saying that he doesn't conceive of mass as being the quantity of matter, which is maybe a Newtonian concept and so on. But I mean, these are sort of concepts for another day. By the way, before we finish off, I'd just like to ask, if some of our participants do download the software and start messing around with it, and they have any questions, can they just refer them to you?
Email me. The programming language that I use, Hot Basic, there is a whole community of very bright people all over the world in every single continent using the compiler, the Hot Basic compiler, and suggesting improvements to it. And there was an active forum where people could pose questions and so forth. So that part of my objective is to encourage other investigators to look at this. Aren't you sort of tired of wallowing around in the unexplained world of the theory of continuous space and time? Isn't it about time to get down to specifics and try to carry this story one step further to a more fundamental level of analysis?
I'm not sure, but maybe in our generation, going back a little time, we were more familiar with high, low-level languages, compilers, and writing programs. We didn't call them code; we were writing programs and so on. Whereas maybe the younger people now are more, they mightn't be interesting compilers. Everything is sort of done digitally on your system, and it's all input there, and the outputs are, coming out, but it's not transparent as to how they're actually working. It's a bit like the old radio sets, with the valves, and you saw how the thing was actually working, but it's all like in a microchip nowadays. So I'm just a little concerned, maybe unjustifiably, but I'm a little concerned that maybe people of the younger generation might not be as au fait with some of these concepts as you and I would be, Jim.
Well, I've been following certain physics forums in the Reddit.com platform, and it's amazing how many penetrating questions apparently young people, or I don't know their age, but I assume a lot of them are young people, and a lot of them say that they are students, in fact, penetrating questions which these folks are raising. But the fact is that they don't have the tools to do more penetrating work into the future. And I might add a pun where you say that everybody is digitalizing everything except theoretical physicists who want to live in an analog world of continuous space and time. That's my little pun. No offense, but I just had to throw that out there.
Okay, we won't take offense. Actually, I was going to maybe just see if there's one or two things left and maybe summarize. But I see Nick Percival has come in to the green room. And Nick, would you like to say a brief word or ask a brief question? If I just... you haven't raised your hand, but if I add you to the stream, either a response or a question to Jim or whatever, Nick, now that you're here.
Well, I wasn't expecting this, so I've pulled down my microphone. I'll ask you a question, Ian. Now that you've become a YouTube sensation and major science influencer, have you figured out how to monetize that fame? Are you going to follow in the footsteps of Franklin Who and retire and in ease?
Actually, has Franklin retired and is taking his ease? I didn't know that.
Well, considering the credibility of my first part of my statement, I don't know about the second part either.
Yeah, okay. Well,
thank you, James, for again talking.
Yeah, you're very welcome.
And I think it's amazing that we have more people going and having their own labs, and now you've got your own software, like Eric Wright's had his lab. So that's a big step forward, I think, for the CNPS. So thank you, Ian.
Thank you, sir.
You're very welcome, Nick. And also, I mean, needless to say, I was going to say this anyway, but we said a few moments ago about promulgating the information and maybe getting input into Jim and so on. Well, I'm actually quite convinced that talks such as today's will enhance that. People looking at our video on the media will no doubt have further questions, and it will, bring things to mind, which, dare I say it, sort of a formal paper would not. And even giving maybe instructions to go into Jim's website ab initio without having heard this might not be so attractive. But I'm sure a lot of people will be interested. The comments actually are beginning to come in now, so I think there will be further.
Yeah, I think having that software lab is just amazing.
Yeah, indeed, it's another thing. Yeah.
Well,
we're trying
with regard to Nick's comments on monetizing an influencer. Thank you, Nick. Let me say that the thought has crossed my mind that it's time for Binary Mechanics Lab, which is what I call my little place here, to get a business manager. For example, the time will come when the software is not for free, but people will need it because they won't be able to do fundamental research without it. And so what we need is a business manager, someone who makes a lot of money who wants to make a lot of money in terms of licensing fees, possible patents, and so forth. Like I can patent certain hadrons, much like people patent certain DNA patterns. So let's get a business manager. If you know someone who's got a business sense and wants to make a lot of money, send them on over.
All righty.
Okay. Well, thank you very much. Actually, I have to come to an end soon. But when I've ended the broadcast and the recording, if Nick or anybody else is still there, I may have a brief word with him. We can do that. But anyway, just offline, more or less. So
Yes.
Thanks very much for that. Excellent. So, so. My pleasant duty is not that we've come to the end of the talk, but it is to acknowledge that we've had a very interesting presentation today. In fact, it's quite fascinating, as I say, the amount of work that's been put into this project in developing the software and in looking at the fundamental processes and in deriving all these constants and the things that Jim has gone through. And as I say, Jim has been very generous with his time. Both in participating in these conferences regularly, which is actually quite important to us. So we have a source of information and somebody we can consult, and indeed also previewing papers and now giving us a more fundamental update on his own system. Actually, he has given talks years ago, maybe some years ago, on the binary mechanics. That's where I first was acquainted with the system. But we thought an update was really appropriate. And he's given us a very good update to tell us what he's been at over the last couple of years, maybe since we last heard on this, because he's been talking about other people's work. So, you're very positive, actually, as well, in that you're totally open to being disproved. You know, the Karl Popper business, that something must be disprovable. If it cannot be disprovable, it's just dogma. So you're very open to that. And you're actually looking at ways where you might be wrong. And you're also... sort of deprecating the throwing your hands up and saying, "Oh, it's just so irrational. We just give up with the scientific method." So you've made that point as well, and I think these are very valuable points, and it'll give us a lot of food for thought in the coming weeks. And I'm glad to say that we've got a sort of an eclectic mixture, different sort of things. We're not just concentrating on one thing, and I think today's talk has been an example, and we'll be following this in the coming weeks. So thank you all very, very much for participating today, and thank you for your questions. Thank you for those in the green room. Thank you very much, last but not least by any means, to Dr. James J. Keene, to Jim for having his patience with
Thank you, Dr. Cohen.
You're very welcome. My services are given with pleasure. I'm learning more than I think I'm putting out. So until we'll be keep an eye on the announcements. I'm not sure exactly where every second week the non-alternative sessions, in other words, next week, where they are. They depend upon what's been happening in the CNPS itself. But do keep an eye on the information. And as far as we're concerned, we'll be sending the information out as soon as we can on what's coming next. So I'll end the broadcast now, and I'll wish you all a very good day. Most of you on the other side of the pond have plenty of time. It's now getting near when I have to prepare for the evening meal. So thank you again, Jim, and everybody. Goodbye.